Today what we're going to be doing is it's two kind of fold goal in the sense that we're going to determine what relationships are linear as well as compare two or more linear relationships with one another. So first of all, when we're looking at linear models, one way we can tell is from a table of values. Okay, and the way we can tell from a table of values, and for some reason that got moved on me, table of values has to do with the fact that their first differences are equal. Okay, you've done first differences before all the way back in grade 9 and again in 10 and 11, and we saw a little bit of that in our previous unit. So when we're talking about first differences are equal, we're going to look at a couple examples and see exactly what that means. So for instance, it says which models represent linear relations and then justify your answer. So we're starting with this little table of values. And before I can even do first differences, I have to check the left-hand column, and that's important. And I have to make sure that these numbers go up an even amount. Okay, now you can see here they're each going up 1. They don't have to go up 1, but whatever number they go up, it has to be the same amount. Okay, then what we do is often are given a table of values and we have to add to it. So I'm going to start another column. I'm going to call it first differences. And what I'm doing is I'm creating like another set of lines in my column over here. First differences, remember we start at the bottom, so 15, and we're going to take away 40. Then we're going to do 40 take away 55, and 55 take away 60. And then when we do that, what we end up with is we end up with our answers, and we end up with negative 25, and this one is negative 15, and this one is negative 5 again. Now, according to this, I should be able to, with a table of values, determine whether this relationship is linear. It is a relationship, but you can see that these numbers are not the same. Okay, they are not the same. So therefore, I say first differences are not constant. In other words, not the same number. Therefore, it's not linear. So the justifying is, first of all, I have to do the differences, the subtracting, and then I also have to say because they aren't constant, it's not linear. So you need all of that in a solution. Now the next example, what they have done is they have given me my table of values horizontally rather than vertically. So the first thing I have to do is I have to take it and turn it into a vertical. It just makes it so much easier to do that. So again, what I'm going to do is I'm going to look on the left-hand column. Does it go up an even amount? Well, in this case, it's going up by 5, so I'm fine. Now what I'm going to do is, again, I'm going to add first differences, and I'm going to start at the bottom and do the subtracting. So I have 135, and again, it just continues. And what happens when I actually do the subtracting this time, I end up with the same number of 45. Now this is important because I'm going up an even amount with my X column and first differences in my Y column are all the same. That means I can say because first differences are constant, therefore it's linear. So I have this as well as my statement. So it's really important that you understand that what we're saying is first differences are always equal for linear relationships. Okay, the next part of what we're going to be looking at is from an equation. Now, when we're looking at an equation of a linear model, again, you've seen this before. We know that the equation can be written in the form y equals mx plus b. Now you know from studying lines before that sometimes it doesn't quite look like this. So really what you're looking for is all of the variables are to the power of positive 1. So my two variables are the y and the x in a linear relationship. And you can see that there is no number with the y. because it's to the power of 1, and the same thing with the x is to the power of 1. So that is really what I'm looking for. Now, the next examples ask, determine which equations represent linear relationships. Now, using this information, we shouldn't have too much difficulty. So, if we look at y equals 2x plus 5, first of all, I have the variables x, and y. You can see both of them are to the power of 1. Therefore, this is a linear relationship. Now, just to be sure, what I've done is I actually did graph them, and I put the graph right underneath somehow, which I cannot click. And I'll look at that in a second. The next one, if I look at it, y equals x squared plus 5. Now, this one isn't linear. Looks very similar, but I have a squared. So because of that square on the variable x, it's not linear. The same is true of the third example. This time x is not squared, but my y is squared. So the both variables have to be the power of 1. When I look at the final example, you can see that I only have one variable, it's y, and it says y equals 6. Now this is linear. It actually is a horizontal line, and you can see that we have the variable, which is only 1, is to the power of 1. Therefore, it still satisfies, um, sorry about that, this still satisfies the variables are to the power of positive 1, so we have the variable is to the power of 1. Okay, and as I said, I don't know why, for some reason, my graphs aren't coming up there because I wanted to prove to you that they really were what I said they were. Oh, there it is, just a small little thing. There's that one, and I would have to zoom it to get the other ones, so if you just wait one real quick. Let's go view, and we're going to go zoom, 125. Do I see it? It is here somewhere. Okay, you can see this one's a parabola, and again, I'm having a hard time seeing these because this one is that horizontal line, and probably if I do this, I will find the last one. Okay, so this one you can see is a straight line. This is a parabola. This one here with the y squared is like half of a sideways parabola, and the last one you can see is a horizontal line. Okay, comparing linear models. So this is just summing up everything we know about linears. Okay, first of all, we can compare the slope of linear models. And what we're comparing is we're comparing the direction. So in other words, is it positive? Is it negative? Okay, so that's one thing that we can talk about when we're comparing. The other thing we can talk about when we're talking about the slope is we can talk about the steepness. In other words, its rate of change. Obviously, the steeper the graph, the greater the number is for our slope, for our rate of change. The other thing we can look at is the vertical intercept. So in other words, this is another word for the y-intercept. And often we're interested in that when we're talking about relationships in the real world. Okay, so it is the y-intercept, and it's the initial or the starting value in a relationship. And finally, we have our summary of everything we know about linear models. So first of all, we know that a table of values, the first differences are constant or equal. The graph is a straight line. The equation can be written in the form y equals mx plus b. Even if we only have one variable, we saw that still works. Okay, the rate of change throughout, if we calculated it, is constant. So in other words, it stays at one slope. The slopes don't change. And finally, the vertical intercept is the initial value of the relationship. Okay, so now it's time for you to do some practicing.